look at Berkeley if you look it up on YouTube.
Let me actually check.
Let me get the link.
Are you live?
Yes.
I want to try to see.
Yeah, so
It's
Audio seems fine.
yeah. Oh, sweet. I wonder if there's a way to get it to turn off the facial recognition square. Yeah, one of these days. One of these days. Yeah. Yeah, I don't know how to turn it off. Just in case people have trouble spotting where you are, hopefully. Exactly. Oh, actually, yeah, you can't tell, but there's a red dot on your forehead. Yeah. Oh my God. But yeah, the audio is okay?
Yeah.
I like it. You gotta get a welcome to my channel kind of thing going on.
Start. So I think we can start. Okay, for today we have a special joint seminar with the nuclear theory group at MBNL and N3AS, group on the third floor. The speaker is Alexander Soloviev from the University of Ljubljana, and he works at a major sector called holography, which is more interesting from our point of view, and also like actual theory of physics. Pretty good coming out. And so today he will give us a talk on relativistic superfluids in extreme conditions. So please, Alexander. Thank you.
Yeah, thank you, Gabriela, and also thank you guys for coming and for the invitation. So, I'll be talking about relativistic superfluids in extreme conditions, as mentioned. I'm going to try to give somewhat of an introduction to the topic, and also kind of connect this to some strongly coupled stuff as well. But this is predominantly based on work that came out in 2020 with my collaborators, and also a follow-up which came out with my master's students. Also a series of work that's I just put on a ton of papers in this direction, but this is with the group at Soloviev, headed by Guarantee, and also by some people in Germany, Adrian Florian, others, Luciauskas, and Northern Rosius in Florence. And yeah, there's also some much more recent stuff from the last few months, including collaborator in Cambridge and Relativistic who's in Poland, so a bit of an international affair. Okay, so I figured it's good to give like a physics motivation. So title is about superfluidity, and that's found kind of ubiquitously all over the place. To kind of ground myself, I'd like to show you a phase diagram. It's really simplistic, one that I use basically in all my costs. So this is the temperature chemical potential plane, varying chemical potential, and kind of in terms of the phase transition, I'm kind of most of the time interested in the chiral phase transition, where you have at high temperatures, and small chemical potential, you start in this unbroken phase where the quark condensate is 0, then the temperature drops, like in heavy ion collisions, there's some cooling, there's a transition of around 160 MeV into this broken chiral symmetry. And an example of that is, there's this nice picture of nuclei colliding, and the search for this critical endpoint that I showed you for a second is the focus of numerous experiments, like the beam energy scan and PAIR, and a whole bunch of others that I just don't list. One of the arcs of my research have been studying signatures of high superfluidity. So, I mean, it's a bunch of works here, but the kind of main upshot is a plot like this, which comes from some people who simulate hydrodynamic evolution, and they compare the results to data. And this is a plot of their predictions. Like some of the predictions are the denominator, and their data is the numerator. And what you see is that this is the yield of ions, soft ions that are produced at a least experiment. And there's this discrepancy around 1.5 times. And one of the things, which I won't be talking too much about today, but this is one of the reasons why there's this enhancement at small pt is precisely reclaimed due to the absence of chiral physics in standard hydrodynamic codes. So that's one end, that's kind of the high temperature end. Then like more lower temperature and high density, superfluidity is found, for instance, in like the upper layers of neutron stars. So this would be something that people can search for through multi-messenger astronomy. Superfluidity is also kind of interesting. I don't know if you guys know about this like notion of arc glitches, but this idea of like you have vortices that form inside the crust and the upper layers of the neutron star. They take in the angular momentum of the system. They get larger and larger, but eventually the whole space gets filled, the whole upper crust gets filled with enough of these vortices with enough angular momentum that the system senses essentially the energy gets too high, and it becomes more energetically favorable for the system to release some of that energy and spin up very rapidly through the whole neutron star. This is what's known as an arc glitch experimentally, and that's entirely due to the structure of due to superfluidity in the material in the neutron star. And then, kind of from a condensed matter perspective, there's this BCS-BC crossover, which is more for superconductivity, but there are these plots from this condensed matter review, where if you go from this weakly bound Cooper pair setting and you start cranking, this is the inverse scattering length, as you start cranking up the inverse scattering length, eventually you have this kind of intermediate regime, which is dominated by a superfluid description. So hopefully I convinced you that superfluidity is found at all scales, or at least all the extreme ones that people are searching for experimentally. Okay, so the big question that I want to talk about today is what role does expansion play on expanding of the system play on superfluidity over a large range of system size and temperature, and what are the physics that emerge thereof? So I mean, I already kind of showed this on the previous slide, but you have systems that have superfluidity at really high temperatures. So this is like gluon plasma, and you have these frigid effects and stuff like this. But also at really cold systems, so really 20 orders of magnitude, you have a very small system size, so on order 10, you have say, I think this is like 5 to 10 fermions that are prepared in an atomic trap. They're then released, and you actually see that they, instead of becoming perfectly spherically distributed, they exhibit this kind of elliptic flow, which is characteristic to hydrodynamic description. And you can also do this with like thousands of atoms that then eventually get this kind of elliptic structure. And people are trying to understand how to describe this from a basic hydrodynamic perspective and in the context of superfluidity. What is the appropriate hydrodynamic description? So what I'll talk about today is I'll give a brief overview of the theory of superfluids. I'll talk about one particular model of expanding superfluids, which is relevant for more higher energies and for larger system sizes. So this is known as Bjorken flow. I'll talk about the mathematical causality stability stability of flows. And then kind of the last thing I'll talk about is the non-perturbative transseries that emerges at late times in the mathematics that are there. So, okay. I think maybe we all know that we can view hydrodynamics as an effective field theory. So here's my cartoon of hydrodynamics. They're just waves that are long wavelength near equilibrium. What you do is you take your conserved operators like the energy momentum tensor, the number current, spin current, what have you, and you expand these gradients. So here I just wrote the first ones, and you say that this is conserved in the appropriate background that you're interested in, and kind of the relevant hydrodynamic variables are the temperature, chemical potential, the flow velocity, and you can kind of package this together in terms of an effective action, which is just some integral over some space-time integral over the free energy over minus the free energy, which is the pressure. And this pressure is just a function of this T mu. Variations of this action with respect to G mu do. This gives you exactly the ideal order energy momentum tensor. So it's kind of neat. And then you can just build up perturbatively all the possible gradient terms. But actually, at the level, at formal level, if you just actually start computing these for different transfer coefficients, you see that this gradient expansion is actually pretty sick. It's actually divergent, and not only is divergent, it diverges factorially. I mean, these aren't the first guys to bring this up, but this is in the context of heavy ions. This is kind of important in the study of attractors. But what you can do this resurgence, resummation business. What you find is that although in your natural gradient expansion, derivatives is written this way, you can instead trace this out for a dimensionless variable, which I call omega here, which is just time times the temperature, and you actually can rewrite it in this kind of non-perturbative way. What do I mean by non-perturbative? So here, this is a perturbative series. This is just an expansion in 1 over omega. But here you have, so this is an expansion for large omega. But here you have a term which is goes like e to the minus omega. And of course, this you can never get from like a Taylor series, right? So this is, there's mathematical techniques which take you from this formally divergent series to something that actually contains non-perturbative effects. So I point you to this article, which was one of the first ones to do this for Bjorken flow. And so that's the story so far for standard hydrodynamics, but I'm interested in systems near phase transitions. And what I'll talk about next is the new slow degrees of freedom enter the system when you're near the critical line. So this is my picture of superfluidity. You have hydro, and now you have other stuff, which is also oscillating slowly, but at a similar scale. So superfluidity is realized, or spontaneous symmetry gradient. Okay. Superfluidity can be realized when symmetry of your system is spontaneously broken. Most commonly, this is U1 symmetry, which will be what I talked about today. So as an example of that, I will refer to my order parameter field, my complex scalar field sigma. Rho I'll call the condensate, psi is the phase. And basically, when you look at your potential over a period of time, so we'll have an evolution in time and temperature, the potential breaks, and now there's a new vacuum expectation value where the order parameter is no longer vanished. And by Goldston's theorem, okay, this implies that there's a massless Goldstone mode, which in the case of for carbon phase transition, these are the ions. You can look at the conservation of your ideal entropy current, because at ideal order, entropy should be conserved. And you get from that this kind of infamous relation, which is known as the Josephson constraint, which couples which relates the gradient of the phase, which can be also thought of as the superfluid velocity, to the chemical potential. So this again links the microscopic, or what seems to be a microscopic feature of your scalar fields to something that's expressly thermodynamic. So these things should be viewed in kind of the same order in the gradient expansion. And lastly, there's this feature which is known as critical slowing down. What that means is, say you're in this kind of situation where you have you're in the unworking phase, and then the system relaxes in such a way that it breaks the symmetry of the potential, and the event kind of rolls down the hill. But the rate at which it rolls down the hill, the relaxation time associated to it, grows like a correlation length to some universal exponent. And that's the correlation length. The correlation length diverges at the critical line. And what that means is that the Goldstone is actually dominant. And in fact, this picture becomes really valid. You really shouldn't be treating the hydrofields in the same kind of vein as superfluid modes. So this should be added to your hydro theory. And what I mean by that is, if you look at the ideal action, you have, again, times the free energy, and there's a temperature and a potential. This is maybe not the most precise. It should be like gradients of sigma, but you will need to add this to your hydro theory, and yeah, your energy momentum tensor. Now you get a correction, so you don't just have the ideal hydro coming from your standard hydrodynamic theory, but you also have, in addition, superfluid component, and likewise, this is the same story for the current. And yeah, and physical realizations of, so by going through all this, you'll see that you develop things that are features that are relevant for superfluids, like sending sound, you'll have quantized vortices, and so on and so forth. Okay. Here, I promise I talk about holography, so here's just an aside, because it's not really what the research that I'm working on, but just to kind of tantalize you with something a bit more familiar. If you want to talk about superfluidity and strong couplings, again, this is due to Herzog and Hartnell and all, but you basically consider an Einstein-Maxwell action with a complex scalar. So Einstein-Hilbert terms, you have Maxwell Lagrangian, the density, and then you also have the complex scalar field with some potential here. And the kind of both fields that you have are metric, you have a gauge field, and you have this charged scalar. Metric satisfies the Einstein equations, and you have also the Maxwell equations. And right. Okay. When you solve these equations of function for these all the fields that you have, and you take the limit when you go towards the boundary, so as that equals 0, you can see that, for instance, like the gauge field, the temporal component of the gauge field has the chemical potential. The next term in this expansion is the number density. This is essentially the J0 component. And yeah, I also write this out for the charged scalar here. If you look at the contribution coming in at z to the delta plus, where delta is the dimension, you see that there's the expectation value of the order parameter, and it goes like Tc minus T. And this is exactly what you would expect in the superfluid theory. So here you have, this is the order parameter plotted against this function of temperature, and you see for a variety of parameters. And as the temperature approaches the critical temperature, it exactly vanishes. That is to say, I think this theory that was studied in 2008, I don't think that this has a dynamically changing mass. So I think you're kind of, they were limited to be entirely always in the broken phase, so they can only come up to T equals Tc. They can't really go above. I'm not sure, maybe this is a question more for the audience. I'm not sure if there are holographic theories that take you above this critical temperature. My talk will be about something about a theory which takes you from the highest temperature into the broken phase dynamically. Don't think there's any reason why this should be possible in holography. But yeah, this is just kind of the punchline is that this describes a microscopic theory for the strongly coupled superfluid. What I'll be talking about is a hydrodynamic theory, so something that's more macroscopic. Okay, so enough of the theory. Now, well, enough of the background. Now about the theory. I'll be telling you about the superfluid model that we studied. This is originally based on the theory of Solomon and Nicolas in 2002, and we just kind of adapted it for superfluids that we're interested in as well. But the basic idea, as I mentioned before, is you have the coupling, so the entire minus the free energy given by pressure plus the complex scalar field. Right, the dynamical variables, of course, are just the temperature and the potential. And you have two components in the complex scalar field, the magnitude, so the condensate and the phase. And what I'm going to do here, this is just the kind of novelty of this approach, is the temperature that appears in spontaneous imaging in the potential, which gives spontaneous symmetry gradient. I'm going to make this space-time dependent. And okay, in the end, I'll just make this temperature dependent. And what that means is that dynamically, as the system goes from, so as the temperature goes from high temperature to low temperature, which is going down the phase line, basically, as the system expands, the temperature will decrease. You'll see that the symmetry gets spontaneously broken in this way. Right. And of course, maybe a criticism that you can have is that you already have a good degree of superfluidity, which is what's known as the two-fluid Landau model. The difference between what the approach I'm telling you about and the Landau model is that in our model, the complex scalar field is actually dynamical, right? It has its own equations of motion. It changes because the system is passing, the temperature is changing, so the mass becomes negative dynamically. In Landau's model, what you do instead is you kind of get rid of these two terms. You just have free energy, and you compute via thermodynamics what is the value of the condensate at a given time. So that is great for basically 90% of systems that you want to study, except for when you are near certain interfaces, when you're in the middle of a vortex, when you have in any time you have essentially large gradients of the condensate. So this is kind of a more complete picture of a superfluid at more extreme edges. So this is maybe a plot that you guys seen already during my other talk, but I kind of just to kind of hammer down the point of how the condensate will evolve. I'm going to show you high temperature, low temperature, and somewhere in the middle will be the critical temperature. So initially you have your condensate, which is denoted by this little blue dot, sitting at the bottom of this potential, which is in the unbroken phase. It just sits there calmly in the minimum. There's a little bit of fluctuations there, but the system is evolving. Then the temperature is cooling slowly, and eventually the potential has changed shape, right? So at some point the mass square term becomes negative, and the condensate is now just really sitting at the unstable local maximum. But there are these thermal fluctuations, and eventually, after the system gets cool enough and enough time has passed, these fluctuations that are here just drive the condensate down to its minimum and acquire some sort of band. So that's kind of dynamically what's being generated in our simulations. Okay. Now you might want to say, a few words about stability and causality. So this is just from my colleague in Cambridge, but so if we want to actually study, so we write down this theory, how do you know that it's actually something that's sensible to do? Right? You're adding to your work, you're adding to your microscopic freedom, you're adding things that are maybe not conserving or maybe violating some sort of conditions of stability and causality. So in order to kind of get around that criticism, you can consider this kind of functional. It's kind of like a grand potential functional, where it's just essentially the sum of the entropy and alpha are Lagrange multipliers, and Qi are schematically all the charges in your theory. And under fluctuations, you require that you're actually at equilibrium. You're actually sitting at a minimum of this potential of this functional. All fluctuations that take you away from that make you go back in. So that this is just a mathematical argument. But the neat thing is that you can immediately, just using these two simple conditions of this functional, you show that demanding the stability, you get that the Killing vector of in your hydrodynamic flow, and you also get for free the Josephson constraint. This is like really a property of the ideal system of equations that I've been describing. And okay, this is a little bit further. Like you can determine what's known as an information current, which is just which is E mu. This is related to the second derivative of your dysfunctional here. And this leads to causality constraints. And then there's a bunch of relations with thermodynamic quantity, second derivatives, and whatnot. The important point is that within the entire domain, the theory is completely stable and causal.
Sorry, what do you mean at the here when you say equilibrium? You say that phi dot equals to 0. This is since your fluid is actually evolving in time. So is this by saying that at some small time window the fluid is not in equilibrium, or is it saying that like the full time evolution, even though it's not 0 and the fluid does change in time, it satisfies some conservation law?
This is more, no, this is really the equilibrium case.
Okay, so in the previous case where you showed us that the fluid just evolves in time, it goes from unbroken phase to broken phase, is not described like this. This is just
These are both. So far, I've only been talking about ideal case. So
okay.
there's no dissipation. Yeah.
I see. Okay, so you have time dependent in equilibrium.
Yes. Yes.
Okay.
Yeah.
So when you expand the hydrodynamics from ideal to viscosity, and you make sure that it satisfies this second the second law of thermodynamics, expansion of the divergence of the entropy current is more than 0, right?
Yes.
And that's how you construct this constituent equation for the viscosity.
Yeah. You can constrain the signs and the relationship between the different principal
Yeah.
coefficients. Yeah.
And then here, you're adding this superfluidity and this addition to mu, and then do you need to constrain, or is this something comparable to that?
So what you do for the ideal case is exactly the same. Is if you compute the entropy current and its divergence, you'll find that it's not 0 at optimal order, and it only becomes 0 when you impose the Josephson constraint. And here, this is the same argument but in reverse. So you have some functional which is meant to describe stable equilibrium, and you're looking at fluctuations around that equilibrium. But then out pops out the Josephson constraint. So these are comparable arguments. This is really hammering the point home. Yeah. Okay. So just kind of as an interesting example from this previous paper with Lorenzo, I want to talk about the superfluid in an accelerating rocket. So what do I mean by that is, let's say you have a box, and it's filled with a fluid that can undergo that can go through a critical transition. It's at some temperature T, it's at rest. And now I want to accelerate it uniformly. And I kind of give away the game that I'm going to play right now, but basically, if you imagine that the system's continuously accelerating in one direction, you'll have a buildup in the back, an overdense region. In the front will be a bit more empty, so there'll be some sort of temperature gradient associated to it, where there might be a critical temperature to engineer things correctly. So you can do this mathematically. You can study this really easily if you just consider the Rinder geometry. So here's a picture of what the geometry looks like. Here's this line element. And all I can say here is let's say there's no fluid dynamics. You're just really studying the evolution of the condensate. Okay, I'll normalize this with respect to equilibrium. The equations look like this explicitly, where R star is some critical value which is associated with critical temperature. And what you get when you solve this equation is this blue line here. This is kind of the result that we have. And you compare this to what Landau predicts. So Landau's theory is that you have essentially, you don't have a smooth transition, you have just a first order phase transition with a really a cusp point, or there's a kink here, at rho equals 20. This is just the value of rho star. In our case, if you actually take into account these, the evolution of the quark parameter, this actually smoothens out, and associated to it is more of a crossover to the phase transition. So that's just like a really Q-tip example, and one slide, one line. Okay, good. So,
Sorry,
yeah.
what about the line, the blue line also goes down, like non theory goes up?
Yeah, that's not super important. So, okay, here it's because this is how you impose boundary conditions. You have to impose boundary conditions such that it vanishes at the walls, so you can't have the thing go on forever. But actually, you see that the region where it agrees with Landau is exactly this intermediate region. And if you take the wall, this wall to infinity, this basically agrees for the whole evolution. The region where it will never agree is in this critical region here. Okay. So, I told you about superfluidity, gave you some background. Now I'm going to tell you about different flows that are interesting. This is more getting towards the API side, so I apologize. But here's kind of a picture of a collision. You have these two beams coming in, they collide, and now I'm just interested in what's going on in the forward electron. So at some one fermi over C, you have this formation of gluon plasma, and so here on the left, I'll tell you what's happening, and I'll tell you on the right what theories you can use to describe this kind of evolution. This is like colored glass condensate, anti-plasma models. Then a little later on, you have hydrodynamization, and kind of in between these two, you can describe this very well using hydrodynamics and dynamical theories like holography. So this is hydrodynamization, so you have a formation of neutrons, and the neutron resonance gas starts to become important. Finally, at some later stage, the system starts to freeze out. This is really the domain of kinetic theory, where you're describing particles that are just flying freely into the detector. And the question that I want to ask is, which geometry do you want to use for collider physics here? So I have a personal preference. So just to show you again, this is the collision. This is usually, this picture is from the Minkowski perspective. A natural one that takes into account this kind of geometry of the forward light cones. So there's a perfect flow given by this line element here, which is again translated between Minkowski using proper time and rapidity. And the kind of game that you play is you say, okay, well, my fluid is at rest relative to this geometry. And what that means is if I transform back into Minkowski, this will give me some sort of non-trivial flow in true flat space. And yeah, this flow is invariant. What's really nice about it is it's invariant in the boost invariance, and it's showing longitudinal expansion. So it's kind of sitting in the middle here, and it's showing how the system is expanding in this direction. And yeah, I just also wanted to point out that these works by Danica Pichetsky from 2005. The holographic version has been known since then. And there's also this Japanese collaboration, which is some pretty important improvements. But that's not the only flow you can take. This is maybe another aside, quite a few. What you can do instead is you can wildly scale your line elements. So just pull out a factor of the proper time squared and work instead in de Sitter space. And this goes back to work by Gupser and Yarum in 2010. And I have a little picture of a slice of where this geometry sits. And why would you do such a crazy thing like this? Well, it leads to an enhanced symmetry. So you have not only the standard boosted variance that you have in the Kirby flow, but you also have rotational invariance around the beam direction, and you also have reflections around the collision plane. And yeah, this holographic Gupser flow, this was due to my colleagues and I back in 2023, a few years now. And kind of, I just want to highlight this is a cute thing that a local in Ljubljana, my colleague Sasha Rosanov noticed. So there's this is really hot off the presses from the last few months. There's another type of slicing that you can take. So instead of it being a spherical slicing, like you can see in this diagram, you can instead take this hyperbolic slicing, right? And this changes the symmetries that you have from SO3 to SO2, and physically what this kind of looks like, this is a plot of the temperature as a function, this is a heat map of the temperature for proper time going in this direction and for radial extension for the radial direction on the x-axis. And what you can see is that the temperature is really just localized entirely along the light path. So this kind of represents an ultra-relativistic shock wave solution. And yeah, just for completeness, here's what the flat space looks like. Because this is really just the three different types of curvatures that you can have. Okay, anyway, this is just an aside. I don't think a lot of people appreciated this, so I just wanted to point out. I'll be now back to the main topic of the discussion, which is dissipative superfluid flow. So, like I said before, you'll now have energy momentum tensor, which will be given in terms of your hydro variables, the scalar energy momentum tensor, and this dissipative tensor computing. So you'll have conservation of the energy momentum tensor. You'll have the evolution of the scalar field, the condensate itself, with this potential containing this temperature term, which flips side, and kappa is dissipative parameters. Then you'll have, I want to work at first order in hydrodynamics, but that's actually in this frame. This is actually a little bit of a sick theory, so we still use the Israel-Stewart equations to kind of cure the sickness of this theory. There's also a lot of work that has been done by this VRSSS paper in 2007. Yes, I'll write the dissipation in this kind of dimensionless way. And I'll work with a conformal fluid because it's much, much easier, where the energy density is just 3 times the pressure, and I'll just characterize everything in terms of the temperature itself. And although I was telling you about superfluidity and the importance of this phase, it turns out that almost the majority of the evolution of this system of equations is dominated by the condensate. So actually taking the limit where the chemical potential vanishes, which is a bit more realistic and a bit more in line with the photon plasma, this is just also, I do this for simplicity for the purposes of this talk. But in any case, it just reduces the number of equations from 4 to 3. And finally, I parameterize my transport coefficients in terms of the temperature. This is the only scale that's left. Yes, but also, sorry, the Israel-Stewart equation, this is the shear viscosity. So the problem is if you just take the energy momentum tensor, I don't know if you know this, just interrupt me. But if you just take the conservation equation with the shear tensor and the shear viscosity and plug this in and try to solve this, you see that you develop acausal modes. So the dispersion relation actually omega grows like K. And the theory just breaks down into V. So to kind of regulate that, you introduce this relaxation time. So if you want to think about this just kind of, so you go from like how do I say this? I mean, you essentially get like time sine omega plus 1 over tau I. This kind of regulates for you this dispersion. So it doesn't just vanish. You don't have divergences. So this is just a feature of first order hydro. This just is for simplicity. And of course, if you go at higher order terms, then this is not an issue. But it's kind of complicated. Okay. So yes, I already told you about Gaussian flow, and the reason why people work with it, besides the fact that it's a really good model for forward lifetime evolution of the heavy-ion collision. But now all of the equations, all the observables in the equation, we just depend on the proper time. So this is just temperature, this is the dissipative parts, and this is the condensative order parameter. So you have your system of equations, and they look like this explicitly. This is kind of a bit of a monstrous set of equations to work with. So, but first I'll just, before I get to how to simplify these things, I'll just show you what a typical evolution looks like. Here in bluish green, I have the temperature, and in orange, I have the condensate. You initialize in some, I don't know, random initial condition. What happens very quickly is the condensate reaches its minimum. It kind of stays at close to zero for a very long period of time. So this is this initial regime. The temperature falls like as you would have in just standard European flow, which goes like the proper times to the power of -1/3. Yeah. This region where this system is evolving, like in European evolutions, we called it the attractor time, and this is around 13.2 fermi/s. We estimated using normal, using phenomenological estimates. So around the lifetime of the ion collision, just around the beginning of freeze out. And at some point, the temperature, we take the critical temperature to be around 1 here. So at some point, the temperature drops below the critical temperature, and the masses become negative in the potential. Now, it takes a while for the condensate to realize what's going on, but you can see that it's slowly rolling down, 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 until it suddenly explodes all the way.
So this attractor time is 15 Kelvin.
Yeah.
It's quite long compared to the scale.
Yes.
And I look at the difference at the hydrodynamic attractor paper, it says around, I don't know, like 5 artifacts or something like that. Is this because of your choice of the question, or?
This is the choice of parameters we
Okay, yes.
use. So I think here we used LHC, like data diverse estimate. And I think if you're, so that means you initialize way higher temperatures. But if you initialize closer to the brick energies, this number goes down. But also at the end here, in heavy ion collisions, you don't have a U1 phase transition, you have an O4 one for the chiral phase, or SU2 cross SU2. So I didn't want to make the statement too strong either way. The dynamics are a little bit different, but just to get a feeling, it's the same order of magnitude. We're in the same ballpark, right? Yeah.
So this is somehow the equilibrium situation.
Yeah.
So if like the temperature is also evolving in time.
Yes. Yeah.
So how do you define the temperature? Is it like some like local temperature? Or is it like,
So if you want, this is really,
evolution?
this is like what we were discussing before. This is really the energy density to the 1/4.
Okay.
So-
So let's just see that for the temperature. You're just saying that the fluid is approximately conformal, and so you're just using that to define the temperature.
That's right. Yeah.
Okay, so then this is one of the evolution of the energy density.
I think that might be a bit,
Okay,
yeah, more precise. Yeah.
and the T critical is the terminal equilibrium, right? So then it's somehow that the T, so in process, the phase transition, because it's out of equilibrium. But the rho at the phase transition should be goes from like 0 to non-zero.
Yeah.
And that's only when I do it in equilibrium.
Yes, and it also takes dynamically time for the potential to change shape enough for the condensate to notice.
I see. Yeah. So that's why then first the rho goes to 0, which is a phase transition, where you restore the symmetry.
That's right. Yeah, so we have initial conditions where your symmetry is not restored, and it doesn't.
Yes. Okay, you restore it, and you stay in that like symmetry restored phase for a while, and then you spontaneously break symmetry again. Yeah. And what is that drives that like spontaneously breaking? Like when you exit that?
As in, the shape of the potential has changed, right?
Because the potential is.
Yeah. So I mean, yeah, it would be great if we had a microscopic theory that actually had this dynamically change it. But this is a model, right? So the mass is set to depend. It's a very well motivated model because you're saying that the mass goes like this is kind of coming from the rising model essentially. It grows like T minus TC, yeah, the mass squared. Yeah. And yeah, kind of the picture is that if you didn't have this order parameter, the temperature would just continuously, because the system's expanding, the temperature would just eventually go to 0, and that's it. But what we find instead is that both the temperature and the condensate attain some asymptotically late time values, which we just denote here as T star, rho star. So this is kind of the picture. This is what you would find if you just put in typical initial conditions. This would be evolution. Okay, so now we understand this late time behavior. This is work from a few weeks ago, actually, 2 weeks ago. Why do you want to study the late time behavior? Well, analytic analysis of late time provides another perspective, in particular, what information from the late time, which is what you're seeing at the detector, what you infer about the early time. The main result will be this novel transseries solution, which I'll talk about at length. And kind of the main driver of this transseries solution we'll see is the C kappa, which is this the parameter which controls the relaxation rate from the unbroken phase to the broken phase. So how the condensate rolls down. And in particular, I'll show you also plots in the boreal plane of these breadcrumbs that form. And what you'll see is that there'll be some that are purely of decay type, so just on the wheel axis. And some will develop quasi-normal-like mode structure, which will lead to some oscillations.
C kappa is what determined that tau sigma from your other plot?
Sorry?
Is C kappa what determines the tau sigma from your other plot?
C kappa is related, yes,
Okay.
but it's not a one-to-one correspondence. You'll see in a second. Okay, so I already flashed you these equations before. Here's a little picture to keep in mind of what the solutions look like. But this is, in general, quite complicated. These are first-order equations. This is second-order equation. Everything's ordinary differential equations, but still, it's a little complicated. So let's throw away a bunch of terms by just saying, okay, we're really at late times. Let's just say the condensate is at its asymptotic value, and let's just take this specific parameter to infinity. So that throws away one equation, throws away a bunch of nonlinear terms here, but it's still two equations, it's still too many. Okay, even simpler, you just take the Navier-Stokes limit, where you throw away this relaxation time scale at all, and you're left with a single ODE, which is just the evolution of the temperature, with this kind of form. And when you take rho naught, so this is the value of the condensate at late times to 0, what you're left with is just the evolution of the temperature, well, just an ODE, which is solvable exactly. So you see, like I promised before, that the temperature goes like the proper time to the -1/3, and then there's a correction due to viscosity. So if this is an exact expansion, you can also add some of the terms as you see fit. For rho naught not equal to 0, so when you actually have this full case with rho naught equal to not equal to 0, you instead have this kind of curious asymptotic expansion, which is the temperature goes like a constant, which is just given in terms of rho naught. You have a correction, which is logarithmic, log over tau, and then you continue like at the next order 1 over tau squared. You now have to go up to log squared, and you have. And this pattern continues indefinitely, so at the next order in tau 1 to -3, you'll have 3 different log contributions, all that are dependent also on the transfer coefficient, which is C. So the kind of general structure changes quite a lot from just being a simple power series, right, in 1 over tau, to now being not only a power series in 1 over tau with a different power, but also having this kind of double sum nature, which also belongs. So we'll be talking about this now. So that's already at the simplest level. So let's go back and go away from the Navier-Stokes limit. So we take C tau to be not equal to 0, and we still keep the condensate frozen. And this is actually the case with rho naught equal to 0. This is what we studied in this resummation of the gradient expansion paper in 2015. This is the second order differential equation that they had. Here's a typical evolution of the temperature. It just goes to 0 at 8 times, and they study the attractive properties thereof. I'm not for the current goal of the talk is to talk about this, but if we add back this condensate for non-zero values, again, you have this early time evolution is identical, but at late times, you start having the temperature approach some constant value, which I've denoted with this orange dashed line. And you can, again, this is just a bit of repetition, but the asymptotic expansion is now a little bit different. At leading order, you have the same as before, as in the Navier-Stokes limit, but now you have contributions coming in from the Stewart equation. So this is C tau makes an appearance. And again, you can do this in a different way. You can kind of reorder it to not be a sum over, so instead of it being log, like a sum of power expansion in polynomials, and summing over logs, we can also sum over logs and sum over the power series. So if we, in other words, I just said that the most confusingly possible, but if we just take, like, for instance, n equals 0, we can just look at the power series that's associated to just rearranging the structure of the expansion, where we go away all the log terms, and you get this kind of, this is taking the root test for different orders in the expansion, and you can see that the terms are growing very quickly. We can take one log and take a look at all the coefficients that are there. So that's this orange line here. And you see that these lines are all going straight up. And in this kind of configuration, so this is tau Tn to the 1 over n, this root test, this indicates that actually this growth is factorial. So we've kind of made the situation worse than before, where the hydrodynamic gradient expansion was diverging factorially. Now every single sector is diverging factorially. So that's not great. But what we're able to show is actually, at least we're able to resum the first transseries sector. So we can look at the temperature and rearrange the series in such a way that we have there's some power, but then there's an exponential, which is non-perturbative, basically. We won't be able to determine this directly from the series. And so it goes like e to the minus tau, which is the standard picture that you have also in this paper called Soloviev. But additionally, you have this kind of correction, which just goes like minus log squares. There's an intermediate scale that emerges due to having this condensate value. And then you have a normal power series, that, as I was describing before.
Sorry, so the new non-perturbative term is this e to the minus log squared.
Yeah, and then you have some key corrections, which are,
But this e to the minus log squared is then a power log in tau, right?
it's like tau to the log.
It's how much for the log?
It's log squared.
Okay, it's log squared. I see. It's tau to the log.
Yeah. So it's something in between an exponential and a power law. Yeah, maybe writing it like this is a bit misleading, but there's some extra scale that appears basically that wasn't there before.
And the lambda, what determines the scale lambda?
So lambda is an integration constant. In principle, if you want to actually match, there's nothing in the theory that tells you what lambda should be. If you want to match this to something in QCT, this would be like lambda QCT or something like this. This is the time scale that you want. Okay, develop it one.
And from the hydrodynamics, you fix it by the initial conditions.
It is fixed by the initial conditions. Yeah.
Okay, so then this effect is e to the minus log squared of lambda QCD.
Kind of, yeah, but I mean, here we're agnostic about which scale it is, so it's. Yeah. So, yeah, as an aside, I just want to say, like, where have we seen this before? This kind of transseries solution. So, an example that I think is really neat is this truncated beta function. So you take like a beta function, expand out to two-loop order. This is, for instance, if you look at alpha s as a function of momentum, this is kind of where it comes from. And you try to solve this equation asymptotically in something that I'm calling suggestively tau. This is not what people usually call this, but just for the purposes of conversation today, which is just log of mu over some characteristic scale. And what you find is also, again, this double sum structure with these log terms at every order inverse power of tau. So what I just said, you get like there's a constant, and then there's 1 over tau, there's a constant times a log, and then there's log squared, and so on and so forth. And this is just cute, because in 1998, these collaborators, what they managed to determine without Mathematica, they managed to do this by hand, they found that you can express this in closed form at second order, it's just exact substitute loop order in terms of a Lambert W function. So this is not to say that this is what we have in our model, but maybe there's hope that you can actually do this recursive summation business also in averages. But anyway, this is just kind of cute. Aside, but you see
This is self-consistent in the sense that G is small, so you're only keeping the first two terms.
Yes.
But this is only self-consistent if like the resummation, like all of the non-perturbative effects that you included, are larger than the free loop effect.
Yes.
Is there any way of knowing that's the case?
No, they literally take this to be, well, no, people have computed in three order.
And then people have checked that this is actually.
This doesn't hold that three order.
No, of course it doesn't hold. I'm saying that if the three loops are small enough,
Yeah.
then the non-perturbative effects at two loops
Yeah.
might be bigger than the loop effect.
I don't know if the three loop effect is smaller, but I don't know if it's small enough to answer that question.
I guess I'm asking if this expression makes sense, not just mathematically, right? Because if you have a series and okay, you resum it, you get some like nice expression. But if you started by some perturbative equation, it might be that the non-perturbative effects you got are actually much smaller than just going to the next order. But I think it's the point that these two different parameters, like G is small, but tau is not small. So you're doing non-perturbative tau
Yes.
is one G.
So G is small when tau is taken to infinity, is the way you should think of this.
Okay.
Right? I mean, this is an expansion in G, right? But all the higher order terms are small when tau is, but I don't know the exact scale at which this is actually, so this is certainly, this argument holds certainly when alpha s goes to infinity, but anywhere, I don't know which finite scale below that. But you're right, this is a bit subtle. But I just, the point of this slide is just that similar asymptotic series have been studied before and have been shown some sort of closed form expression, at least at this order loops. Okay, and so now I'm kind of getting towards the end of my talk. This is back to the full case of the Bjorken superfluid. So now I'm just solving for dynamically these system equations, all a full shebang, for different values of this condensate for the specific parameter that's associated to the rolling of the condensate. And you see this is kind of very cute. You have for small enough values of C kappa, this is some sort of underdamped oscillatory regime. So here is the condensate rapidly picking up value. You can kind of imagine that it's coming down to its minimum, like the right-hand minimum, and it's oscillating back and forth. So this is underdamped. There's also a very reaching the minimum, which is given by C kappa is 8/3, and then there's the overdamped C kappa is equal to 10. So it's this kind of thing you understood also from the undergraduate class in classical physics. But there's a natural critical value of the condensate relaxation, which is given from this in terms of the initial condition parameters. And for these plots, this is just C kappa is 8/3. And I'll show you how we determine this on the next slide. So this is now a bit more involved, but the kind of snapshot that you can take is you have your temperature, you write it in terms of a perturbative series, and then there's the first transseries, which contains these corrections, which go like e to the minus tau minus log squared. And so now if you just imagine in phi 1, there's an expansion also in logs. Let's take the part which is independent of logs in this sector, just for illustrative purposes. We can do a Borel transformation, which is this filter. And then kind of look at the A approximates and look at where the poles are as we increase the order of these A approximates. So this is like the worst approximation. This is one step better, and so on and so forth. And it starts to approach and form essentially a density of poles. And this branch point that's associated to here, we actually know analytically this is given by these parameters here. And what we find is actually for C kappa larger than C kappa star. So when you're in the unbroken, when you're in the overdamped regime, you find these parameters, which are just given in terms of the transport of your hydrodynamic theory. But if you're in the underdamped region, you find that these branch points actually start, so they actually come from minus infinity. They come in and they actually separate, and you find that they start accumulating in the imaginary plane. And these are actually quasi-normal mode-like, as promised. And if you want to find the state thirds, then for the parameters I showed here, it's whenever the square root becomes imaginary, right? So this is, you just check really quickly that this is just given by C cap is equal to state thirds. Okay, and so now why should you care all about this? Well, to kind of conclude, just as a snapshot, again, here's the picture of the numerical solutions. I'm looking at the underdamped plot here, which is just shown here in red again. So you have these oscillations that are characteristic. You can take the transseries solution, which is some complicated mess, and fit from asymptotic infinity, and with this blue dashed line. And you see that although we're only taking a couple of terms, I think this is like 4 terms, we're actually able to capture basically a couple of many oscillations that are also increasing in size. And yeah, okay, that's a technical argument, but yeah, what I want to just say is that there's excellent agreement up to early times, down to even where this is a completely different regime of the superfluid evolution of the condensate, which is exponential, but even down to that regime, the oscillations are captured quite well by the transseries solution. So I realize I'm just a bit out of time. I'll just leave you guys with a couple of questions that I'm thinking about still. So what is the possible phenomenological inference of these condensate oscillations in particle spectra? So you see similar oscillations also when we do lattice simulations of the all-4 critical phase transition that's associated to chiral phase transition. So far, I've only been talking about the U1 case, but what about for pines? Are there some sort of, is there an analytic structure for that C2 plus C2 case? This is kind of a cute thing that I was talking to some people in SQM about last week, but this notion of disoriented chiral condensate is an idea that was really popular in like the early 80s and 90s. But the idea is like you have a heavy ion collision. There's system is evolving. There's this fireball that's expanding, and in the center of the fireball, so here you can see this is like for high temperatures, you're in the unbroken phase. But if the condensate doesn't decide to roll down to the true minimum, it can roll down into a false vacuum at some intermediate temperature. And in fact, this is pointing in the higher direction. This is in the direction of condensate. And in fact, there's this U1 circle that's here. You can just kind of fall to one of these points and just sit there. And in that sense, the condensate is disoriented because it should be oriented towards just the condensate direction, but instead it also sits in the pine direction. So people were talking about experimentally observable effects. Back in the 90s and early 2000s, there wasn't enough data, and people didn't quite understand what they were seeing. Now it's maybe the situation is different, so hopefully this is something that we can actually see in experiment. I kind of hinted at these other flows before. Maybe this is something that's worthwhile to explore in the superfluid context. Yeah, and kind of these larger questions of like what are the larger mathematical questions of these log transseries. What can we find to determine any resurgence relations that are maybe also relevant for quantum field theories? And yeah, and finally, I mean, this is really like future thinking is looking at superfluidity, also a neutron star, I should say cross, but yeah, it'd be interesting to see these effects if they all start persisting in dense nuclear matter at a dense temperature. So thank you for your attention, and hopefully there's some
So yeah, we have a date after the seminar, so you think because of the theory both usually have like cookies or cake or something, so we're gonna have outside after the seminar. And yeah, are there any other questions?
or long term in the talk. So,
All right, so let's thank again our speaker.